Hello everyone, my name is Emilio Ribasti. I'm a PhD student at the Intelligent Autonomous Laboratory in Padova, and today I'm going to present our work titled Graph-Based Optimization Framework for Hand-Eye Calibration for Multi-Camera Setups. So what is hand-eye calibration? Well, it is the process of computing the pose of the camera with respect to a given reference frame that could be robot manipulator based or an effector. Why is this important? Well, it is important because if we want to control a robotic arm based on visual information, we need to know these transformations. There are two types of setups. We have eye-based, where the camera is mounted on the robot, and we have eye-hand, where the camera is mounted on top of the robot. Typical approaches have the problem that is strongly dependent on the PMP algorithm. That means that they are not robust to visual noise. So there is a state-of-the-art approach that is also robust to visual noise, but only covers eye-hand setups. So our contributions can be summarized as such. We cover the complementary ion-based single camera setup. We further extend to multi-camera setups. And then we offer an open source implementation of the pose method. To solve the single camera ion-based calibration problem, we use the same tools that are used to solve SLAM problems due to similarity between the two. We have some fixed parameters that are the camera intrinsics and the 3D checkable points, and then we have some state variables that we want to estimate. So one is the checkable pose with in respect to the end effector reference frame, the camera pose with respect to the world's reference frame, and the checkable pose with respect to the camera reference frame. And the last one can be seen as trajectory because we have M, if we have M measurements, we have M state variables we want to estimate. The first error that we want to minimize is the chain equality error that imposes the chain equality constraint that simply states that the chain of transformation on the left is the same as the chain for transformations on the right. And these are the state variables that participate in the minimization of that error. Then we have the reprojection error. That's simply the minimization between the distance between the detected checkable corners and the predicted checkable corners given the current estimate of the checkable in the camera reference frame. So we want to solving the single camera ion-based calibration is the same as finding these transformations that minimize this cost function. We further extend to the multi-camera scenario. We see that our graphical formulation becomes more complicated. The fixed parameters, we just have a slightly difference that we have now and different camera intrinsics. And as state variables, now we have one state variable for each camera for the camera pose in the world reference frame. And now we have the checkerboard has n trajectories because now we have n cameras. And we have a new state variable that involves the spatial relationship between the two different cameras. So first we extend the chain equality error that simply is stacking the different chain equality errors for each camera, and the same for the reprojection error. What is game changing is the cross observation error. So what is a cross observation? Well, it simply happens when we have two or more cameras that are able to see the checkable at the same instant. This is encoded by a co-visibility matrix that is equal to 1 when two cameras are able to see the checkable at the same time, and 0 when it doesn't happen. And this co-visibility matrix activates the cross observation error that simply states that given that we are in camera 2, we are able to predict where camera 1 is going to detect the checkerboard's corners. And this is due from the current estimate of the checkerboard in camera 2 frame and the relative transformation between camera 2 and camera 1. And this is the new cost function that we want to minimize that is very similar to the previous one, even though if the terms have slightly different meaning. We can see the results of these through our experimentations. We first experiment on a simulated environment in gazebo, in which we have ground truth and we are able to control the level of the noise that we add to our experiments and the effect. The first comparison that we do is graph multi up against graph single applied n times, and we can see that the cross observation term is actually helpful because graph multi always behaves better than graph single. And then we compared it against the state-of-the-art methods that are open source. And we can see that for translation noise and rotation noise, our method performs as good or even better as the other methods. While for visual noise, our method is the only one that is able to converge. Same was confirmed by a real environment experiment that we did in our laboratory. There is no ground truth, so we use the reprojection error as a metric of goodness results. And we can see already from the image that camera 1 and camera 3 may be affected by the lighting conditions, and this can be seen through the results that there are many methods that for camera 1 and for camera converge, where our method CAF multi is always able to provide the best solutions. With these, the conclusions are that we are able to, we extended successfully one to cover the complementary setup. We've successfully exploited multi-camera scenario characteristics. And we proved that through our testing that our method is more robust to visual noise than any other method. Thanks for your attention and see you at the conference.